Hello, everybody. I'd like to welcome you to the CMI webinar series designed for our CMI constituents and by them as well. As we get into the webinar, for those of you that have been on multiple times, I just want to remind you a few things about some of the logistics. We are hosting this webinar from Colorado School of Mines, and we are always looking for other topics. And so if you have anything in mind that you'd like to hear more about or a specific project, please let us know. Also, this is a public webinar, so it will be archived. And this is in the aimslab.gov/CMI under the workforce section. And if you go there, you can access this in about a week. Questions, they're going to be held toward the end so that our presenter can get all the way through his presentation. And at that point in time, we will open it up for questions and answers, of course, Q&A session. I really encourage you, however, if you have a question, to go ahead and prepare it, type it in the Q&A section there so that it's queued up and ready for the actual Q&A session. I'm going to introduce our presenter today, and from Los Alamos National Laboratory, it's Dr. George Guthrie. He's the Deputy Program Director of Applied Energy Programs at Los Alamos. His PhD is from Johns Hopkins University in Mineralogy and Geology. And he's been a scientist for over 30 years with a very broad portfolio that you can see his technical background, what it spans, and you're going to hear a little bit about that today. What I like is that Los Alamos National Lab gets to have him twice. So he spent 19 years there, took a stint with Nettle, Department of Energy for 6 years, and is back again at Los Alamos. So I don't want to take any additional time from our presenter. George, I'd love for you to take it away here if you are ready.
Great. Thank you so much, Cynthia. And I will take it away. So thanks, everybody, for the time today. And I look forward to telling you a little bit about Los Alamos and what we're doing in the area of critical materials. And one of the hopes here is to give you a better insight into what we're doing so that we can pursue opportunities for collaboration. So I'm going to start with, I'll have three different sections in the presentation. I'll start with talking a little bit about Los Alamos as a lab to give you a little sense of who we are and how we approach the work. There's three things that I'll try to emphasize. One is that in the area of energy and including in critical materials, what we try to do is leverage our capabilities that we need for our core mission in NSA. In the critical materials area, that boils down into two main pieces. One is the unconventional separations, and the second is revolutionized measurements. And both of these are important, we think, and I know that you all think as well, in terms of the supply chain for critical materials that we'll need as we transition energy. And the last bit I'll try to emphasize on the lab overview is our tradition of partnering, and in particular our engagement with students and postdocs and their faculty members. The second part of the talk will then transition into looking at a few examples of what we're doing in the area of critical materials. And you can see that these overlap very heavily with things that are being done in CMI. I'll start with the research and development piece. And then at the last part of the talk, we'll shift to the deployment piece. And I'm going to do that in the context of looking at what we're exploring in the Intermountain region relative to a CO2 economy, which we think has intersections with critical materials. And by pursuing this intersection, we think it's a way to help both CO2 and critical materials deploy. Okay, so first a little bit about Los Alamos. If you haven't been here, this is just to get you oriented. We're in New Mexico, northwest of Santa Fe. And you'd fly into Albuquerque, which is the main town in New Mexico. And it's about a 2-hour drive to get from Albuquerque up to Los Alamos. Los Alamos is on the flanks, the eastern flank of the Jemez Mountains, which you see here in the background. Los Alamos National Lab is just south of Los Alamos, the town site. The Jemez Mountains are sort of interesting. They're on the western side of the Rio Grande Rift. And so you see in the map this picture of the Rio Grande coming up through the middle of New Mexico. And there's actually active rifting going on, so New Mexico is being pulled apart. Part of that results in volcanic activity. And the Jemez Mountains, on which Los Alamos sits, were a volcano, the remnants of a volcano that erupted about 1 million years ago. And so these linear features you see with the town site and the lab are actually mesas and canyons that are formed by the tuff, the volcanic tuff that was erupted from this volcano. Los Alamos, the town is just on top of the mesas. Los Alamos National Lab is actually on both the top of the mesas and in the canyons. It's one of the biggest of the national labs. I think it's second only in size only to Sandia, which is also in New Mexico. We're a multidisciplinary lab with a very broad science, technology, and engineering workforce, a lot of experimental and computational facilities, and nuclear facilities as well that we try to leverage. You see some of the stats on the lab down in the lower left, and the one I want to call your attention to is the last line, which shows you the number of students and postdocs, and in particular that number relative to the 8,900 employees at Los Alamos. So of that 8,900, roughly 40% is in the science, technology, and engineering side. And so you get a sense of how big our student and postdoc program and engagement is. In fact, it's one of the biggest of the national lab complexes. I think Lawrence Berkeley is slightly bigger because they benefit from being co-located with University of California, Berkeley. But we're very proud of this large postdoc and student pool. And it's one of the prime ways that we like to collaborate. So we collaborate with these students even when they're at their universities and with their faculty members who also can have appointments here. There are other ways, though, that we also collaborate, and this shows one of the other pathways we use, which is in consortia. These are the consortia in the energy area that we're involved in currently. A lot of these are multinational lab and university consortia, and they also interact, the consortia involve heavy industrial interactions. And so lots of ways we like to work with our partners on trying to develop new innovative technology and then move that forward to the market. Los Alamos is organized like many of the national labs in a set of technical divisions that you see on the right-hand side that mirror, in many cases, what you might see at a university. So we have divisions like bioscience and chemistry that we would see that are common in universities and other national labs. And then we have divisions also that are more unique perhaps to the Los Alamos operations, like accelerator operations and nuclear engineering and non-proliferation. So if when you collaborate with Los Alamos researchers, they will reside in one of these technical divisions. But the way we approach the work at the lab, we believe very strongly in the culture of multidisciplinary approaches to solve the challenges we need to solve for our core mission. And so we promote that at the lab through these things called capability pillars. And these are areas where we have to excel and innovate in order to achieve our core mission. Each of these areas is a multidisciplinary area, and they're the areas in which we invest internal funds, both in terms of internal R&D and facilities. And so I'm going to talk about two of these, science of signatures and complex natural and engineered systems. We have much of our critical materials work falls in these two areas. So science of signatures is about finding new ways to detect and monitor signals of interest, particularly in natural systems. Complex natural and engineered systems can go all the way from an engineered system from a power plant down to a process that involves multiple components. And so in this case, it would be our separations work. So we're a national security lab. We're part of the NNSA within DOE. But nevertheless, we have a very vibrant energy portfolio and have had for a number of years. You see some of the energy program areas that we're working in here at the lab across DOE. I'm going to talk in particular about work we're doing in fossil energy, and the reason for that is this is where most of our critical materials work that's coming from the outside is being supported. So some of this is coming out of the carbon storage and utilization program in FE, and some of it is coming out of the new program that FE has formed on critical materials. And the emphasis of that program really is on critical materials, particularly rare earth elements, but even other critical materials from unconventional resources and how might you recover those. So that gives you a sense of what we're doing or what Los Alamos is about. Now I want to transition to what we're doing in critical materials, and I thought I would start here, which is a graph that's showing the fossil fuel use over the last 100 years, and these fossil fuels now are cast in terms of the CO2 that they produce. And so it gives you a better way to be able to compare across these. And you know what you see here is we've had 100 years of being able to use fuel that's relatively easy to pull out of the ground and relatively easy to use. In the last 10 years or so, 15 years, let's say, since 2005, we've seen a reduction in our CO2 emissions from the 2005 level to what you see at 2019. And that reduction has been almost exclusively driven by this increase in the natural gas you see at the bottom, the blue curve. And that was driven by the deployment of hydraulic fracturing and horizontal drilling to release the gas that's contained in shale. And so that growth in shale gas has led to this decrease in the use of coal primarily, which has led to a decrease in our CO2 emissions. What's important here is if we think about the goal that President Biden recently laid out of reducing our emissions by 50% by 2030, from that 2005 number, you get to this green star. And what's really important for us all to remember about that green star is that getting to that green star cannot simply be just a continuation of the glide path we've been on. We have to have a much more concerted reduction in our emissions over the next decade to do that. And to achieve that reduction, critical materials technology is going to be central to that. And I know that's something that you all are familiar with. We're real excited about the goal the president has laid out because we think it provides urgency to the work that we've all been doing. So I want to look a little bit at some of the critical materials technology we've been doing at Los Alamos. And what you'll see is, we've been focusing on these two areas. The upper left-hand area is on separations and recovery. The lower left-hand area is on analysis. And we think both of these are important for increasing the supply chain of critical materials as needed for EV, expansion of EV in the auto industry, being able to lead ultimately towards new materials for using energy and storing energy and so on. One of the things that I was really struck by when I began looking a little bit more in detail at what's going on in CMI is how many overlaps there are between what you're seeing on this left side and what is going on with the CMI. So I think it's a very encouraging piece for me in terms of exploring collaborations where we can further our work even more expeditiously through these strategic collaborations. You can see that in the area of separations, we've got a broad set of things that we've been doing already internally for our nuclear mission. And these we're bringing into the critical materials area. This includes tailored ligands to be able to mobilize critical materials, particularly F elements. Some of that mobilization is from oxides and metals, but we have a very big non-proliferation piece that requires us to be able to mobilize those from silicate-based materials as well. We've been exploring temperature-driven approaches to be able to recover and concentrate critical materials. We've been looking at a number of different supercritical fluids. CO2 is one that we think is particularly interesting, and we've had some work on that, looking at tailored ligands that would mobilize the critical materials into the supercritical CO2 fluid. And the last bit, so those first ones are obviously at the lower technology readiness scale. They're concepts, they're bench scale R&D that we've been doing, synthesis and testing. We also have work going on at the higher end of the readiness scale in terms of process intensification and looking at different ways of incorporating these new technologies into a process workflow, and how do you make that workflow more efficient. On the analysis side, one of the reasons we're doing this is Fossil Energy had asked us to look for a field-based method for being able to do rapid screening of rare earths, in particular in complex media, things like coal-based products, maybe fly ash or acid mine drainage. And so what we've been doing there is, and I'll show you a slide on this one as well, is looking at a laser-based method that combines both a chemistry approach and a mineralogy approach. So you can get the chemical and the phase information from that in the field. All right, so this is sort of a thumbnail overview of the kind of work that we've been doing in the areas of separation and signatures. I'm going to look at 3 vignettes here to give you a better sense of a few specific projects that we have. And I do see, by the way, there's a question in the question box. I'll come back to that at the end during the Q&A session. Okay, so the first vignette is looking at our need to recover. I've already mentioned that we have this need to recover particular F elements from complex media. And one of the particular applications is over on this left-hand side, is the nuclear fuel cycle and non-proliferation. And so that in particular has driven us to look at how can you recover these F elements, including both actinides and lanthanides, from media that you might collect at a site where you have suspected activities going on. And so the concentrations here would be very low. This is an analytical method that we've developed to get to be able to get quantitative recovery of materials from things like clays and other types of soils. We've approached that by using ammonium bifluoride to be able to pull the rare earths out of these various materials, including refractory materials. This has been very successful in our analytical work for nuclear forensics. And so, and the reason we believe that's successful is that there are a couple of aspects of ABF that are particularly interesting. One is it is a fluorinating agent. And fluorinating agents are very important for being able to loosen up silicate-based materials without the need for hydrogen fluoride, which is typically, or hydrofluoric acid, which is typically used to be able to attack these. So ABF allows you to do this in a way that's much safer and cheaper. It also helps to lower the reliance on harsh acids like very concentrated HCl or nitric acid. And the other piece is that ABF is a known complexing agent for actinides. And so the thought was this would also be a good approach for the lanthanides. And so we've been extending this with our work for Fossil Energy to look at recovering rare earths from fly ash. And we've had very good success with this. This is near quantitative recovery of lanthanides using much lower acid concentrations. We've looked at different, how this changes as a function of different types of acids, different concentrations of acids, what's the optimum reaction time. And we think through this, we're now heading down a path that can transform the way material is recovered from these types, rare earths are recovered from these types of material by making a process that's safer, that's cheaper, and that has higher efficiency of recovery. The contact for this work is shown at the bottom, George Goff here at Los Alamos and his team. Next example is a slightly different strategy in terms of recovery and separation of rare earth elements from complex media. And the issue here is we've had a lot of investment recently in trying to understand the behavior of actinides and lanthanides in high temperature, high pressure aqueous systems. There are a number of reasons for this for our core mission. I've shown some of these here. That's driven us to do a lot of internal investments to look at things like better thermodynamic measurements of the species that will be existing under these conditions. And so that we can use that information then to explore ways you can exploit the different behavior of the aqueous species as a function of temperature, as a way to then separate these in a supercritical fluid. So on the right-hand side, I show the extension we're doing. You can see at the bottom a graph here that shows the behavior of these various lanthanide complexes in an aqueous system as a function of temperature. And what you can see is different behavior over this temperature range. And it's exploiting that behavior in a chromatographic process that we're now exploring as a way to separate lanthanides very effectively using this aqueous process. There's several contexts for that. Artas Mikdisov, Hakeem Bukhalfa, and Robert Currier. In addition to looking at the recovery in the context of recovering the lanthanides, the other piece that we've been using the high temperature system for is looking at desalination of brines. And so Robert Currier is the primary contact for that piece of the work. Last vignette I'll give is on our analytical work, and I mentioned this briefly in the overview, and that is we need to be able to analyze in the field, and field being written very broadly, a number of materials in complex media, and a lot of these materials tie around our core mission, so that the nuclear forensics piece requires us to be able to analyze for actinides and lanthanides in these complex media. That's shown as that backpack unit for LIBS, which is laser-induced breakdown spectroscopy for the IAEA. The other extreme in terms of field scenarios is Mars. And so this is a unit that we've designed that's now been up on Mars, analyzing soils for both the chemistry and the mineralogy. And so this is combining now LIBS with Raman spectroscopy to be able to get the phase information from that. And so that's all covered in this center section on the approach. So in addition to this, to development on the laser piece, the other piece that we've had to do is to understand how you convert those complex signatures back to analytical information that you need. And so there's been a very heavy development of machine learning tools to be able to take those raw signatures from LIBS and Raman and convert them to the kind of analytical information we'd need. So we've been extending that in the right-hand side to develop a field portable unit for analyzing rare earths in fly ash and other unconventional sources that are relevant to the fossil energy portfolio. And this shows one of the initial spectra now in terms of the LIBS spectra on a fly ash. And so we have a lab set up that we've already done to be able to extend the machine learning protocol so that we can do the analytical reduction. And we're in the last stages of then assembling this field unit, which we hope to be able to test in the summer. So the final contact is Sam Clegg. There are a number of other things besides separations and analysis that we're doing in rare earths. I'm going to focus on these last two here because they segue nicely into the deployment piece. First bit is on combined processes. And as I'm sure you all are very much aware, unconventional resources that we might go after, something like a fly ash, can be economically marginal for recovery of critical materials. And so the one question we've been asking is, how can you improve that economics? And we think one way to do that is through combined processes. So one example I've shown here is on desalination. So if you're desalinating a brine, because you need to do that for CO2 storage, in that process, you could have a co-process that recovers the lithium, and the combined economics for desalination and lithium recovery is something that helps to improve the economics. Down in the lower piece, we've also been looking at unconventional resources for fossil energy, and this includes fly ashes. I've shown some of the regional fly ashes we've been looking at in the map in the lower right with the numbers. The inset shows the Buell Park diatreme, and so another piece that LANL has been exploring for CO2 storage is conversion of a low-grade ore like a diatreme into solid carbonates as a way to permanently sequester CO2. And that can be a little bit more expensive than putting it underground. And so we've been asking the question, how do you improve the economics of that? And one way to look at that is that diatremes can be very enriched in both rare earth elements and platinum group metals. And so the co-recovery of those is something that we think can help to improve the economics. So all of these things get to this question of how do you take the R&D that we've all been doing and begin to get to deploy in an incredibly accelerated time frame. And part of that is through getting the economics right. And we think there's an economics in terms of cost. We think there are other aspects of economics that can also help, and that's in particular playing off of the relationship between supply and demand. And the example I'm going to show here is what we've been looking at in the context of CO2. And you'll see that there are ties between this and the rare earth piece that I'll touch on as I finish this up. So the CO2 challenge is that the Department of Energy has spent a couple of decades and a couple of $1 billion developing the technology to show that you can capture CO2 efficiently at concentrated sources like power plants and other point sources, and you can store that CO2 underground safely if you, in some areas within basins within the United States. The problem is we've had 2 decades of research, and yet we see very minimal deployment of this. And there's been some early deployments that have led us to the realization that if you don't have a reliable demand for the CO2, you simply cannot capture the CO2. You have to have somewhere to be able to put that CO2 and use it. And the demand has come in the early projects from enhanced oil recovery, which is very much at the whim of the oil market. So we've been looking at other things for building the demand side of this equation and getting that up in a very robust portfolio of CO2 demand, which then provides a pull for incentivizing future capture, which then provides a portfolio of capture, which helps to stabilize new sources for demand. What's interesting about this is shown in the bottom, and that is if you take both supply and demand and you look at the economics of that, you can generate this new economy that goes somewhere between $50 a ton CO2 if you're treating the CO2 as a waste to $250 a ton if you're using that value-added products. And so we've asked the question, what could that be? What does that look like at a regional scale? How might you actually deploy it? And so we've been looking at, we started looking at least at the 4 corner states, Arizona, Colorado, New Mexico, and Utah. And what becomes very interesting in this context is we think there's a credible technology pathway to getting to 300 million tons a year of capture and utilization, which would make these states carbon neutral. You can even then go carbon negative if you can, in parallel with this, begin doing fuel switching. The reason the CO2 economy, though, we think is very important is shown at the bottom, and that is that 300 million tons a year could represent somewhere between $15 and $75 billion per year in terms of an economy. And what an important metric for you to know about is that the fossil economy in these 4 states is about $40 billion a year. And so if you can begin getting value-added products with that CO2, so you move to the higher end of that range of 15 to 75, you can have a transition pathway to take communities that have depended on fossil fuels and transition them to a new economy based on CO2 as a backbone. And so we've been looking at that in particular in this region and asking the question, what would the portfolio of supply and demand look like? And it moves beyond the conventional point sources and storage to the things you see in the brackets. I'm not going to go through these in detail, but you'll notice that some of these are small uses. For example, low water agriculture could be using CO2 as a way to spike and seed the growth. It's not going to use 300 million tons of CO2 a year, but it can be very regionally important for this area in terms of transitioning to a new agricultural economy based on low water methods. Some of them are big enough that they can call it the CO2. Repressurizing reservoirs, for example, is one of the things that could be done. The other thing I want to point out here is there's this synergy in the blue box, which is that CO2 economy. If you look at those various pieces, you see that it's symbiotic with a hydrogen economy, a bioenergy economy, and a geothermal economy. And so we're trying to understand how this synergy across these economies can be exploited to be able to accelerate the deployment of each one of these in the region. The other synergy that we think is really intriguing, though, is the one with critical materials. And so this is showing some of the ties here between the CO2 economy and the critical materials economy. So I got three categories. There's recovery of critical metals, recovery of critical materials like helium, and recovery of water. You can see schematically where these come from and how they tie to the various pieces of the CO2 economy. So natural gas in this region is contaminated with CO2, which has to be separated and used in some way or stored in some way. But it also contains, in many cases, very enriched deposits of helium, which can be co-recovered. On the CO2 storage or CO2 injection, to be able to do that at large scale, we believe you need to produce the brine with that. And if you're taking that brine and then desalinating it to produce water, there's a critical materials piece with lithium that comes right out of that. And the last example is the unconventional resources that I talked about with mineralization, fly ash, kimberlite, and so on. So that gives you a sense of what we're doing in the R&D area of critical materials. It gives you a sense also of how we're trying to approach the deployment. What is it we can do to incentivize a rapid deployment of the R&D that we're doing and getting them into these economies? We look forward to exploring areas that we can collaborate with CMI in helping to move these things forward for the country. So with that, I thank you for your time, and I'm going to turn now to some of the questions. There's several that have been posted in the Q&A box already, so I'll just read these out and then answer them. The first one is from David Reed. Do you know how much CO2 is generated for electricity for an EV versus CO2 generated from a similar gas-powered vehicle? And how would other fuels compare, for example, biofuels, methane, and propane? And a really great and meaty question, David, and one that I'm going to punt on because I don't have the exact details for you in terms of life cycle analysis on all of the things you're looking at. I will sort of say a couple of things. One is that I think part of your question about the EV versus CO2 from a gas-powered engine, Cynthia is going to answer this question live.
No.
Cynthia, did you want to?
No, actually,
that's for
you. That's for you, George. I'm going to just make sure that I finish it for you in the end. So continue on.
Okay. You've asked a really complicated question about is it better to move to, let's say, electricity that's initially derived from coal and maybe being transitioned to natural gas in the near term versus doing the internal combustion engine. And I know there's been a lot of work done on that in terms of life cycle analysis, and I can try to get you the information and get you a link for that. And so just send me an email if you could remind me. I'm geo@lanl.gov, and I'll I will try to work on that. Next question is from Daniel Ginasar, and the question is, let me get my glasses on so I can help to read that. Coal and fly ash have very low concentrations of rare earths. Have you found higher concentration of sources from fossil plays? Very good point, and that gets right to the heart of the question of the low economic potential for some of these unconventional resources. Part of it also is we think that there's been a lot of work done on both fly ashes and on materials that are associated with the mining of coal, whether it's an acid mine drainage or the material left over from above or below the coal that's been mined, where there is variations in concentrations of rare earths. Part of what's not known is how this is systematic in these systems, and so the reason we've been designing this LIBS backpack unit with Rahman has been to provide a field method for being able to do screening that then allows you to pre-select samples that you're going to pull back to the lab for analysis. And so we're hoping that when we get this field unit up and running this summer, that we're going to be deploying it at a number of the coal-related sites within the Four Corners area. So this ties to the third question from Eric Schwegler. And the question is, I believe INL has worked on developing a portable LIBS device through CMI, and I think I remember seeing that as well. And we look forward to exploring where your work and our work might be complementary on that. Certainly one of the things that we have tried to do is to, in addition to the LIBS piece, which Los Alamos has a very long history in LIBS. In fact, I think the term was coined at Los Alamos originally, and we've been using this largely for light element analysis in the past, and our work more recently has been focusing on these heavy elements. But the other piece that really became apparent at Mars is you also wanted to be able to analyze remotely the phases in which these materials lie. And so it's this combination of LIBS and Raman that we think is really important, and we'd be interested in talking more with the CMI researchers on this and seeing where we might be able to go together. Next question is from Beachlin Nguyen, and do you have a contact for the INL portable LIBS device? And I don't have a contact for the INL portable LIBS device, but if somebody has one, that'd be great. The contact for the Los Alamos LIBS device is Sam Clegg. Next question comes from Scott McCall. What makes CO2 superior to other gases, such as air, nitrogen, et cetera, for the suggested applications? So in the case of, I guess I'll answer that by thinking about why are we looking at CO2, or why have we looked at CO2, supercritical CO2, in the context of our recovery work in actinides and lanthanides. And there are a couple of reasons for that. One reason is that you can get to the supercritical region for CO2 at a pressure and temperature that is readily achievable, and in a way that you cannot for nitrogen or water. And the reason that getting the supercritical region becomes important is that the properties of the supercritical fluid enable it to have very good permeation within a material, very good coverage. It's got properties that are similar to a liquid and a gas, and you can take advantage of those combined properties to be able to enhance the separation and recovery. The other reason that CO2 becomes really important in these contexts, especially in a mixed context where you might have another fluid, which is an aqueous fluid, is that the CO2 will remain as a distinct phase from the aqueous phase. Most of the material transport in the kind of systems that we're looking at occurs in the aqueous phase. So in other words, you would typically dissolve rare earths and other materials into the aqueous medium, and it gets transported in that medium. And what it means is that if you can get tailored ligands that help you to mobilize something like a rare earth from the aqueous system into the CO2 system, it's a way to separate materials that are dissolved in the aqueous medium very effectively. And then it's a very simple processing. You can take the supercritical CO2 out, and then you can, what we've looked at is running that through a nozzle that has a hairpin turn on it, and so you can take advantage of centripetal forces and separate out the rare earths as a function of mass, and as you're flashing the CO2 to recover them. So that's why we're looking at CO2. Let's see, Beachlyn has another question here. Where do you consider CO2-driven turbine technology as part of securing future energy? Really great question, and one that I'm not an expert to be able to answer. I know DOE in a number of the program areas has been looking at supercritical CO2 as a working fluid in these engineered systems, including turbines, and I don't know, I can't give you a distinct answer for that. I will say that we've been looking at it not in the context of an engineered system, but looking at CO2 as the working fluid for subsurface systems, in particular geothermal heat recovery. And CO2 has we think, has a very distinct advantage there because of these supercritical properties, and because it allows you then to recover more of the heat energy, because you can take advantage of the phase changes in that. And I'm sure that's the same kind of process that's being thought of and used in the turbines. But if you send me an email, I can also get you some better contacts if you're interested in the point where the supercritical CO2 is being used in turbines. David Reed has a question. What is the mechanism with ABF and rare earth recovery? Or how would this differ in action from hydrofluoric acid? So the ABF, we think, works in two ways. One of those is in a fluorinating way, and that's the same mechanism that the fluorine and hydrofluoric acid functions for silicates. In other words, the fluorine ion is able to attack the silicate structure and open it up to be able to recover the rare earths. The second way is in complexing into the fluid once the silicate is opened up. Also something that happens in hydrofluoric acid. The problem with hydrofluoric acid is it's a really challenging material to work with. It's got a lot of safety concerns. There are cost issues associated with that. And so what ABF brings in, we think, is a cheap way to get the fluorine ion into the system to be able to take advantage of its properties, but do it in a way that minimizes the safety and cost issues that are associated with hydrofluoric acid. Next question, and it looks like it's the last question at this point, is from Eric Schwegler, and it's just a reference to the LIBS INL contact. And Eric, thank you so much for being able to track that down and send that to me. And before I get rid of I see that there are a couple of emails that have been put in the chat, the Q&A box, and Cynthia's removed it, so I can't see those. So Cynthia, if you could actually send me the email contacts that were put into that Q&A box, that would be great. I'd really appreciate that. And with that, if there are any other questions?
Yes.
I don't see anything in the chat.
And we do have time for a few other questions if we get those. But also what I'd like to say is, again, thank you so much for such a great presentation, George. It was nice to hear what Los Alamos Laboratory is working on, particularly in the areas of separations and recovery, and also your field rapid analysis tool that's potentially going to be ready. That is going to be incredible. And this also gives our group of CMI nationwide many areas of thought for collaboration. And indeed, there were several emails in the answered questions. We'll make sure that we get those to you. Also, I think you're going to hear from more individuals. So I'm looking at the very last deal here. And George, did you have your email on there? Just want to double check.
I do. It's simple.
Okay, fantastic.
It's geo@landl.gov.
Oh, there you are. Great. Okay, perfect. Because I know you're going to hear from several other individuals. But it does look like, even with this pause, that we don't have any other additional questions. So again, I'm going to leave with a thank you. And I'm also going to remind our audience again that this is a webinar series that occurs monthly. This recording will be available next week at aimslab.gov/CMI, again, under the workforce menu, and I think you're getting used to that. Please let us know if you have suggestions for a future webinar topic or presenter. Next month, join us on June 16th for the Strategic Opportunity Framing for Technology Commercialization. And it's going to be presented by Julian Kenrich and Ames Laboratory and Ellen Coppersmith, Decision Frameworks. Details are going to be published, of course, in Critical Times, and you can always find it at the aimslab.gov site, again, under the workforce menu. Thank you all for your attendance, and we look forward to seeing you again next month.